Hey, welcome back. We'll first talk about how to get rid of randomized signatures using just a PRF, and then we'll talk about how to apply this for the tree-based construction in order to make it not just not random anymore, but also stateless. So we'll start with the signature scheme pi-base, and for simplicity, let's assume that the sign algorithm of this signature scheme uses at most n random bits. Then we also take a PRFF. And now we construct a new signature scheme where essentially we are generating a normal key pair, but in addition we generate a key for the pseudonym function. Now the secret key is just the key for the pseudonym function plus the secret key for the signature scheme. The public key is as before. Now to sign a message, we run the sign algorithm as before, but now we feed it with randomness from the PRF. To be more specific, for every message m, we get a pseudonym string fk of m, and that one we are using for signing message m. In particular, if you would call the sign algorithm twice, you will get the same signature each time. Verifier works as before. So now, let's prove that if f is a PRF and pi base is secure, then pi is also secure. As usual, the first thing that we need to notice is we have a PRFF in here. And the magic power of a PRF is that we can replace it with a random function and nobody will notice. So as we did before, we can just define a conceptual scheme that works like this scheme here. But this one will use a random function instead of a pseudonym function. Now we know that the chances of A winning against the conceptual scheme versus this pi scheme that we're constructing, the difference in winning probability is negligible. If you want to show this formally, you can come up with a distinguisher D that essentially runs A against the signature scheme, but instead of using this value fk of m, it will query its oracle, which is either a random function f or the pseudo-random function fk. And then if it's the f function, then for A it will look like it's playing against this conceptual scheme. If it's this fk function, then for A it will look like it plays against the pi scheme. And then D can just output a bit indicating whether or not A wins. So if A would win more in this one word than in the other, then D would output one more in the one word than the other, and then this difference wouldn't be negligible. But we know that it's negligible because it's a pseudonym function, so that's it. So then essentially, this conceptual scheme, this is basically the base scheme, but essentially if you query for a signature on message m a second time, you will get the same signature as in the first query. For the first time you're querying for message m, you will get a random value f of m as randomness for generating the signature. So everything is exactly as in the pi base scheme. You get a properly random string as input, or like as implicit input for the signing algorithm. And when you then call it the second time, you will just get the same signature again. So if you think about this, this cannot possibly help an adversary in winning against the pi concept scheme. Why? We're just giving the adversary against the pi concept scheme even less information from signature queries than he would usually get. So he only gets one random signature, and then repeat queries for the same message are basically useless. Can you formulate this more formally in like a reduction kind of way, saying that if we had an adversary against the pi concept scheme, then we could build an adversary against the pi base scheme that would win with the same probability? Yeah, so essentially our adversary against the pi base scheme would wait for signature queries from the adversary against the pi concept scheme. Then if the adversary against pi concept asks for a signature on m for the first time, the base adversary will just ask for it and relay the result back to the conceptual adversary. And if the conceptual adversary asks for a second time, then our adversary would just block this request and just answer with the signature that he answered with for the first time. Then for the conceptual adversary, everything looks the same. But if the conceptual adversary outputs a valid forgery, then also it will be a valid forgery for the base signature scheme, and then everything will be fine. So that's already it. And all of this means that de-randomization for signatures is just a thing that we can do. If we have a randomized signature, we can always just throw a PRF at it to generate the randomness, and then we get a signature that is not random anymore. So now let's look at this idea of de-randomization for tree-based signatures. If you remember in the lecture, this is the way that we used in order to get stateless signatures, all of these tree-based signatures. And there are essentially two ways to look at this. So the one thing is that you can think of the state as just storing all of your random choices that you did before. Okay, so essentially the state just makes sure that if you've once generated a public key for some node, so let's say this one, that you never have to generate it again, and that you always know this is the public key that I used to use for this position. And this is very important because the signatures that you use in this tree constructions are one-time signatures. And so in particular for this pk epsilon, for example, it will sign these two public keys, and you need the state to make sure that the public keys that you're signing, they're always the same. And so you just remember the public keys. And then you can think of the PRF as saying, okay, now I just need a way in order to make sure that I can consistently compute the same public keys again. So in this way of viewing it, you don't need the state anymore because you just generate everything new, and you use a PRF in order to make sure that everything that you're generating new, you use the same randomness to generate it again so that you will get the same result every time. There's a different way of looking at it, which I think would make the security proof for this more easy. And that is that as a first step, notice that in this tree-based construction, we could get rid of the complete state if we just compute the full tree during key generation. Obviously, we can't do that really because this takes way too long, but kind of as a conceptual scheme, we can think about this. Then we just store the whole tree in the secret key, and then that's it. Now, obviously, we don't need any state anymore because we can just look up kind of everything in the secret key. Now, as a second step, we can think about each node in this tree. And each node in this tree, so this full tree that we generated, will contain a key pair and a signature. And now we can notice that we can replace essentially this key pair and the signature by just the randomness that we use to generate them. So let's say for every node, we generate the keys with randomness R, name of the node, so the randomness we chose for that key generation. And the signatures we use some other randomness for. And now the idea is that if I just store the randomness, I don't need to store the public key and secret key, and I don't need to store the signature, because I can always just run the key generation again, and I can run the sign algorithm again with the randomness that I've stored. So if you want to look at it this way, we've just found an equivalent way of representing the values stored in this tree. We don't represent them by the actual value anymore, but just the randomness that we use to create it. And now this is kind of the clever part, which we've seen before multiple times now. If our secret key is just a huge list of random values, well, we know how to compress huge lists of random values. We use PRF. So essentially, we would run key generation now with just FK. And for generating the signatures, we may also need randomness. I mean, Lamport scheme doesn't need any randomness, so if we're just using Lamports, then we don't actually need this, but maybe we do. So we generate this as randomness also using a pseudorandom function. Mind you, we need a different pseudorandom function because the randomness for generating the key and the signature, they should usually be look independent. Just that in the lecture, instead of using two different keys for those two pseudorandom functions, because we want them to model different functions, because for the same input, they shouldn't output the same random string. In the lecture, instead, we kind of prefix the input to this function with a constant that indicates whether or not now this is supposed to be a pseudonym string for generating keys, or if this is supposed to be a pseudonym string for generating signatures. So essentially, instead of FK prime, we would just do, and then just to make this argument easier, we also just prefix all of the other invocations. And if you think about what happens if you replace this one pseudonym function with a random function, then essentially now you've made from your one random function two random functions. Because now you're essentially looking from just having this one random function. You get essentially these two random functions. So the trick is, because values that you put into this function f never collide for different invocations between fkey and fzig, you get fresh random values every time. So even if you've queried for fkey on position 15, then if you query fzig afterwards for 15, it will be a completely different value because the input that you give this random function is completely different. It's not completely different, it's different. And so it will give you a different, properly random value. So that's just the trick that's applied here to make this proof a little bit easier, because now you don't have two pseudonym function and two pseudonym function keys, which would also be provable. But now you have only one pseudonym function. And if you replace this with a random function, then you essentially get these two random subfunctions that will give you randomness that's independent for key generation and signing. So that's already it. So if you look at how you would prove this, in the first step, basically you just write down the scheme differently. But if you're an adversary, you don't know whether like the signature that you're querying was already stored somewhere in the key generation and generated there, or it was just freshly generated and then put into the state. Everything looks exactly the same whether or not you generate everything in the beginning or not. So that's just like rewriting the scheme and doing nothing. Then the second step is also just rewriting the scheme and doing nothing. So for the adversary, it still looks the same. And only in the third step, we're doing something. We're replacing this stuff by a PRF. But we know how to prove this. We've just done it, and we've done it multiple times in this course. So actually, this is not hard. So essentially, no polynomial time adversary will be able to recognize whether or not it's playing the signature game against the signature that we had in the second step, which is the same as like this tree-based signature, or the signature scheme in the third step, because the only difference is that there's a PRF in one of them and the other one uses proper randomness. We could define a distinguisher that would output whether or not A wins in this game, blah, blah, blah. This is the same as always. So this is how we de-randomize tree-based signatures. And in this case, we even get this nice benefit of getting rid of the state. Because depending on how you want to look at it, either you use the PRF to get consistency in regenerating all of the stuff that you would normally store in the state, or you can think about it like computing the whole tree, getting rid of the tree computation results and just storing the randomness, and then compressing this randomness heavily using just a PRF. Okay, now questions for you. Two of them actually. The first one is, can we also do a similar trick for chain-based signatures? So could we just apply a PRF to chain-based signatures, basically using PRF of I to generate the ith key, and some other PRFs, let's say value at I prime, as randomness to generate the ith signature. And so then the idea would be we don't have to store all of the key pairs and signatures in the state anymore. We can just like regenerate them. So does this actually work? Okay, so the problem is for chain-based signatures, you can't necessarily do this. you could get rid of the part of the state that remembers the signatures and the public keys and secret keys that you've used. The problem is that also in the state we had these messages that have been queried before. And you had to remember these messages too, because they were part of signature verification. So whenever you gave out a signature, you needed to give them all of the messages that have ever been queried before. And for these messages, you still need the state. They are not random. An adversary gave them to you somehow, and you can't just replace them with a PRF. So that's one huge advantage of this tree-based construction, because there the state does not contain the messages. And the second question is, this de-randomization trick kind of seems useful. So for signatures, we can just make sure that they become deterministic and everything still works. Can we apply a similar trick to CPA secure encryption? So instead of having a randomized encryption algorithm, we would just compute the randomness that we use in the encryption algorithm as PRF of m, therefore making the encryption algorithm deterministic, essentially. So does this work here too? So the fun thing is the answer is yes and no, but mostly no. So we obviously we can do this and everything would still be correct. However, if we do this, then obviously everything also becomes insecure. As we've learned, deterministic encryption is not a good idea. So if every time I encrypt a message, I get the same ciphertext for it, then CPA attacks become just very easy. So we can do the same trick, we just shouldn't. All right, so that's already it for using PRFs to de-randomize stuff. Thank you for watching this, and see you.